Well, you know what? We may as well get started. So, because we're already recording, we're already rolling. Hi everyone. Apologies for the noise if it's cutting through. Um, they're doing roof work at my building, and they just started directly above my suite, like 5-10 minutes ago. So amazing, perfect timing. Um, so practical rateless set reconciliation. A lot of us are really excited about this paper. It's been going around. I was on a call yesterday where people were like, have you heard about this rateless reconciliation paper? I'm like, yes, I'm running a session about it tomorrow. So, and talking to other teams that are also doing sync protocols about it. Not all of them are choosing it for a variety of reasons. But I think it's like a really, really interesting approach. And when I first read it, I think it was Philip maybe dropped it into the Philip Kruger dropped it into the Vision Discord. It just blew my mind. It's like this really nice confluence of factors. And I know a bunch of us on this call have looked at synchronization mechanisms and set reconciliation and invertible Bloom filters and all of this stuff before, but it didn't really like gel. And this seems to have like a really nice set of factors. Again, there are some drawbacks to this technique, but Brendan, would you be willing to give us a quick rundown of how this whole thing works before we jump into conversation?
Sure. Thank you, Brooke, for continued hosting of the Distributed Systems Reading Group. But yeah, to do a quick overview of this piece of academia, I think a lot of us have been wanting to use Bloom filters in reconciliation for a long time, or we have been, and there's been a amount of work there. And so the general problem here, Alice and Bob have two varying sets. We need to figure out and transmit the delta as efficiently as possible. And we specifically want algorithms that are defined on the difference between those sets. And that's sort of the core that this thing gets at. And sort of before this paper, I think a lot of the Bloom filter-based approach was kind of sitting in this moment of needing to know the answer before you can do the answer, right? You needed to effectively estimate the difference between the two sets so that you could appropriately size a filter such that it would give you a really efficient, compact expression of the delta between the two things, such that you could reconcile on either end of the wire. And what this paper sort of does in such an elegant way is all of the prior academia around Bloom filter, including invertible Bloom filters, is based on using a uniformly distributing secure hash function as its mechanism of distributing inside of the filter. This paper takes the notion of, takes a lot of sort of inspiration from the world of erasure coding and just posits, they kind of quote unquote do the work. They go deep and figure out how to use a non-balanced hash function and instead tinker with the way that elements are distributed into the filter such that it is rateless and has no parameters to it. And the way this thing works at a high level is you just grow the filter until it inverts. And so it's building upon the world of invertible Bloom filters such that what you were looking for is a pure element in a delta between two filters that are constructed to represent both sets. And once you find that pure element, a pure element is where there's only one entry in a slot. And then you use that to perform a peeling process and recover values from the encoded filter itself. And this paper just basically says, okay, cool, we're just going to grow them over the wire until it inverts. And we're going to do that, you would need to have in hand some sort of mechanism for encoding any amount of elements into any size of filter in a way that is uniform and parameterless. And they've figured that out here, and they have a technique that approaches that. Yeah, it's the literature puts it into the origin or the necessity for this work comes from the blockchain space. And so they put themselves into contrast in comparison with existing block syncing state or block syncing mechanisms from Ethereum and Bitcoin. They make it clear that Bitcoin's pin sketch based approach is actually faster, but that this uses less computational complexity. And when you compute these filters, as long as your set doesn't change, you can reuse that for reconciliation across multiple peers, which is a really, really, really nice property. That was really fast, but like those are kind of the high level bullet points on the paper. And I think from there, maybe that's my gobbledygook version of an intro to this paper. and then maybe just go from there. Is that right, Brooke?
Yeah, absolutely. So the only thing I would add to that, like, and what I love really about this approach is essentially you're saying, like, we're going to start with really coarse grains. Like, here's everything compressed with an XOR, whole thing in a single element. And then we're going to refine that over time. And when you get to the level of refinement that you actually need, then we can stop and you can just pull all the values you need out of it using a peeling decoder, which is pretty cool. And yeah, so I'm actually curious because obviously I know Number Zero looked at this because Brendan put out a really nice summary on YouTube about it. But have you actually tried using this like for real? There's a Go and Rust implementation.
And 3/4 of a TypeScript implementation because I had to get those animations to work, and it was pretty hard. So we've looked at it very carefully. The techniques that we use inside of IRO, which is the principal stuff we work on at Number Zero, is based on range-based set reconciliation from Alyosha Mayer and co. We are not yet using it. There's currently an active investigation into using rateless IBLTs inside of the binary trees of the reconciliation process. We haven't gotten there yet. I have not yet gotten to formally plugging this into anything yet. We took a good hard look, and I'll be blunt, the Rust implementation is nice, but it's quite academic. And so it's not yet like prepped for production use. And so we're still very much in the evaluation phase, but everyone remains pretty excited about the work. The question is just figuring out when and how and where to plug it in. You don't plug it in just because it's shiny. You plug it in because you think you're going to get some perf win. So we're still at the perf win evaluation phase.
Cool. So before I start going into my random thoughts on this, because I haven't actually used it like in production, but I've been playing around with the idea of it now for what, a couple months. I'd like to open it up to others, questions, comments, concerns, thoughts. Remember correctly, Brent, you had some, you were excited about this paper a couple weeks ago. I can do my usual trick of just sitting here in silence until somebody says something.
Can you tell us about the downsides? I want to hear the antithesis.
Yeah, sure. So overall, I'd say very, very, very positive, right? You can do one-way reconciliation, which is amazing, which is a problem that a lot of these other mechanisms just can't handle, including the set-based, a bunch of the other set-based reconciliation mechanisms. You have to go back and forth, right? And the thing that kills you in a distributed system isn't bandwidth. Bandwidth is like massive these days, especially when you're dealing in sets, just identifiers. It's latency. And so all of those extra round trips can get expensive. So being able to just send things one way, really nice. The biggest downside, so near the end of the paper, they start talking a little bit about fault tolerance, right? I'm not sure if I'll be able to find it actually. Yeah, resistance to malicious workloads. They never say this is a Byzantine fault tolerant mechanism. So unlike things that are based on hashes in particular, this is not Byzantine fault tolerant. You can create a stream of values that never ends, or the one that they mention in here is having hashes, finding hash collisions on the 64-bit tags, so that you either have to now deal with 256 bits and increase the size of the stream by 4 times, or have the shorter inputs, shorter outputs, the 64 bits that they recommend here. But it's not just that. It's like, what if your count's completely wrong? What if you say, oh yeah, no, it's totally this, you know, the same values that were there before, plus maybe one element. But we claim that it's 100 million elements that are in there, right? Or whatever, right? And you'll just never finish. At what point do you stop? Like, and suddenly now you have to start making all of these extra decisions that are not problems that you have in a Merkle search tree. where you're going back and forth on it, because at some point you're going to bottom out on 3 images, right? It might take a long, even then, I guess it could conceivably take a long time, but if it's a tree, then you need to generate an exponential number before you bottom out, right? So like they're more BFT than this. And so that's actually been a blocker. A few teams I've talked to. So I was at Local First Conference a couple of weeks ago, a bunch of people looking at this paper. And is it Byzantine fault tolerance kept coming up as the big problem. And that's it's not really, like, they talk about it being an incremental structure, but it's kind of not, because you can't cache up until this point and then start appending more elements later. You have to take the entire thing and add elements across the whole filter. I think that there's some bounding on that. So they don't really talk about it in here, but when I think about it, you should be able to send more than one element at a time. They talk about it like you're sending a single, element, and then you're told to stop, right? I think basically you could batch it in whatever, a megabyte, of ranges, and then you could even make it static and just have it sit on a server somewhere and say like, yeah, give me, ranges 1 through 10, and I'm happy to take 10 megabytes of this. And it could, like, you could run it as a obviously it's online because you're pulling it, but as a non-interactive protocol. Totally do that, make it super cheap, cache it, all of this stuff, right? But now when you want to add anything to it, you have to rewrite that entire structure. So you cache and validate the entire thing, which also kind of like, it's not really a weakness because it's only at write time, but anytime you add anything to your structure, you have to recalculate the whole thing. So if you have something that has a lot of updates to it, you're potentially updating the structure very, very frequently. So now you're thinking, start thinking about things like, well, I'm going to break this up into 2 stages. I'm going to have my in-memory stuff that I'm doing, and my reconciliation mechanism is going to be behind, or I'm going to have 2 of them, of the old stuff and the new stuff, right? And so it's kind of like it feels like I kind of want a little, in an ideal scenario, this work is already amazing. They even in the algorithms, they're like performance tuning it, using variable length encodings, all of this stuff, right? But it feels like, I just want, like, in my ideal scenario, I just want 1 or 2 more things in here to make this work. And so being a Bloom-based approach at all means that it's automatically not BFT, like instantly. Is that a problem for every use case? No. And could you use like other kind of committing protocols on top of it? I guess so, but now you're adding additional overhead. So those are the main drawbacks. Howdy group today.
I put something in the chat. Basically, I don't know, a confession that I still wanted to participate, so I basically sped read the paper and got the difference part, and there was some curious number they got to by a Monte Carlo simulation to get to 1.35. So Monte Carlo simulations is like you have a random number generator between like 0 and 1, and it just feeds those numbers into what, a formula somewhere, or what, and it's that 1.35, or it just,
Yeah.
I guess this is one question. How does actually did that work? No, that's a simple question.
How did the simulation work, or how does the
How do you do the Monte Carlo simulation to get that probability difference of convergence of communication?
I mean, Brooke, you might be able to correct me if I'm wrong, but if I understand correctly, they're just basically doing sets with random sets with different with a preset known difference, and then resolving those and checking what the overhead is, and just to like basically run the algorithm through its paces and show what happens, and you get this diagram figure 4 here, where you have an interesting like range of outcome possibilities in the that fat thing on the left side is basically how lucky are you going to get, because there's a ton of values crammed into the filter. Every single value is represented in the first element of the filter always. So if you're lucky, you get a quick inversion and you'll get a really fast reconciliation. But generally, as the set difference gets larger, it trends towards this 1.35 number.
So does that include like the peeling, or just that you need to do the peeling, or?
So that's the definition of the overhead of the data over the wire.
Okay, so that's a different animal.
Yeah, so it's like if the total size of the difference in bytes is 100 kilobytes, you have to send on the order of 135 kilobytes of data.
Okay.
It basically has like a third overhead, one way of thinking about it. Yeah.
Of the difference.
Of the difference.
Not of the sets. Yeah. So you could be syncing 2 gig sets, and if the difference between those two 1 gigabyte sets is 100 kilobytes, then this is the magic, right? The magic is having that defined over the delta, not over the size of the sets.
Are they just randomly sending this data over the wire, or what's the pattern there?
So this is just an empirical test.
Okay,
right?
okay,
So
yeah. I mean, the Monte Carlo is, but the implementation of that would be different, right?
Yeah.
So
it's a Bloom filter that like tapers, like every element goes into the 0th, and then each element that you're putting into it has its own little generator function that spreads them out over time, and that is deterministic based on the value. Basically, you use the value as your own random number generator. And then, go ahead, Brooke. Sorry.
Yeah. So the Monte Carlo side of this is just an experimental setup piece. There's nothing to do with the actual underlying algorithm at all. The underlying algorithm starts by having a very coarse-grained, here's everything in one element. And if I get just that one and I have the same stuff and I XOR those together, I'm going to get back a bunch of zeros and go, oh, okay, I have everything. Great. If there's one element difference between our two XORs, when I XOR them together, I'm going to get back that one element. And based on the count field next to it, if it's plus or minus 1, I know if they have an extra thing or if I have an extra thing, because I know which way this is sitting, right? If we've diverged and we both have elements that the other one doesn't have, I'm going to get back some kind of gibberish out of that XOR process. I was trying to say, okay, I need to go a little bit more granular. So in a Merkle-based situation, now is where you'd go, okay, our Merkle roots are different. I'm going to go down to the next layer and see if we have like which elements are different so I can explore that subtree, right? In this case, we say, okay, give me another element of XORed things, but just some of them, right? Give me half of them XORed together. And we have a deterministic process. So based on the same elements, it'll always be the same value for the next element to show these are the elements in that portion of the subtree or in that, part of the sets. I XOR those together and I go, oh, because it's a smaller set, here's just the one that's different, let's say. And then I know what that one element is. I can go back to the coarse-grained one, pull that element out and go, am I now able to read from this, unreadable, XORed thing? I've now pulled another element out, I've peeled it out. Can I now read any more elements from the coarse-grained thing? Yes, great. No, okay, well then I need another element and I'm going to do this again, right? Until I can then peel out all of the values. So it's also a compression technique, which is kind of cool. The Monte Carlo stuff is just there. So they did a analytic study on what the overhead should be, which is how they get all these formulas. And then additionally, they test it empirically. So the back half of the paper, because it's like 19 pages, this paper, right? The actual algorithmic portion of it is like the first, like what, 5, 6, 7 pages. Yeah. So the first half, a little under half the paper, the first 40% of the paper is like, here's some algorithms. And then the back half of the paper is, and then we actually tried it out on a single core 2016 era, why 2016 era single core machine. Seems like a random number to pick, but sure. I guess that's what they had on their laptop, right? And we got these particular results out of it, which matched our analytical, like the formulas that we had derived. So to double check that their analysis was correct. And they found that their worst case scenario in practice was 1.72. And the smaller the difference, the wider that variability may be. And then it converges to 1.35 over time. Okay. And so that's how you get this very wide in this purple diagram here. You get this very wide range at the beginning, and then it kind of converges down because we start to, as the number of elements changes, the overhead becomes more consistent because like it's deterministic, but it's using like a pseudo-random process. Basically.
It's probabilistic and deterministic, which is funky.
Yeah. Well, pseudo-probabilistic, right?
Touche, right.
Yeah. And so after about 1,000 elements in set difference, you get this really just like perfect straight line at 1.35. But also on really small sets. So here we are at, 1 or 2 elements. Sometimes the overhead is actually less than a single element, right? So like, it's just, there's this really big difference and then it gets really small very quickly, which is what you would expect, right? If you have some random function and there's only 2 elements, well, there's more likely in your Monte Carlo simulation, you're throwing balls into buckets. It's more likely that you're going to throw a ball into an extreme bucket. But over time, you're going to get a really smooth function.
Oh, that because you're sort of kind of learning over time, or
because over repeated iterations, you're going to, so if you think about a bell curve, for example.
Okay, yeah.
Right? It's most likely that you're going to hit the middle, but you're going to kind of spread across it, right?
Okay, so it has nothing to do with knowledge, it's just has everything to do with like probability.
Yes, yeah, exactly.
And 2 kinds, right? The probability of the simulation and the probability of the inversion of the filter, of the algorithm. And so like, I think Brooke was pointing to the probability that like when you're simulating, you're going to pick bonkers numbers. So you're going to get wild results at the job. But then the more numbers you pick, the more uniformly, the more correlatable, whatever I don't know. Somebody uses smart term here. They look more predictable. It's easier. Yeah.
But it's just like, if you've ever, I can't remember the name of the mechanism, but you can get these, it is a physical demonstration of a bell curve, where it's just a bunch of balls, and then you throw them through a slot, and it just pings across these pins, and it produces a perfect bell curve every time. But like, how does that happen? Well, it's just the probability is that they're more likely to end up in the middle than on the edges. There are some that are on the edges. And so it's just the same mechanism here.
Yeah, it's just like an hourglass or something with a bunch of sand. It's going to pile up in the middle.
Yeah, exactly. Yeah. But not all of them are in the middle. Some of them are on the sides.
Right.
Right. So if you put a single grain through, that single grain could end up anywhere. It's just more likely it'll be in the middle. And so when you put the entire hourglass through, there's a spike in the middle. And that's all that they're saying, is that spike is at 1.35. So a third overhead. Which feels like a lot, right? Like, if
you think it's a lot? A third overhead of the difference? I was like, that is vanishingly small. It's bonkers.
I'm saying a third feels like a lot. It's way better than anything else we have, right?
So these are percentages. Third of a. No, it's not a percent. What's the maximum that you could have in overhead?
So you have 35% overhead of the difference between the sets in communication cost. So if I have two sets that are each 1,000 elements, but they only have one set difference, I'm going to have to send one message. And I'll get back. Everything else is the same except for this one element. If it's 1,000,000 items in each set and there's 1,000 difference, I'm going to have to send you 1,350 elements to reconcile 2,000,000 elements with each other.
All right. I mean, this doesn't sound terrible.
Yeah, no, in practice
Dude,
it's very good.
It's like
It
legit
sounds
fire.
incredible.
It's
Yeah.
it's as good as it gets. Well, pin sketch is better. Pin sketch is also extremely hard to get my head around and requires a silly amount of upfront computation and is per reconciliation based. Session state is very high, whereas this is generic. The other thing to really point out here that we haven't talked about a little bit is the actual design of the algorithm is totally generic. So all sets, there's only one. There's no parameters. You just put stuff in and grow it. And that's, you grow it. You can grow forever. That's the rateless part. But like in all other, I think some of the other things you run into a lot of in this Bloom-based approach to reconciliation is you have to spend a lot of time thinking about parameter tuning and getting smart about parameter tuning. This is gone here, right? Like it's just send me stuff and I will yell at you when I'm done. And that's a really, it seems like it's a byproduct of hacking into the hash function that you use. And the way that they use the hash function we should probably just visit that for a second. I think there's a really smart trick buried very deep in there where the element itself is used as the seed to a random number generator. And that's how you get this, because you need a very specific curvature of probability for the actual spacing of elements, right? Because we want every single element to always map to the 0th element, and then it needs to be unique per element, some decreasing probability of mapping to any given thing. So the paper goes into a lot of work to do two things. First, to like figure out how to do that in the first place, and also how to get that to not be super computationally expensive. And so they go through, and I'll be honest, this part I glazed over a little bit in my work because in the presentation of this, because it's complicated. It involves estimating sort of the next appearance in a sequence that you would normally compute, which is sampling from a larger set. And that academia went a little bit over my head, to be honest. Yeah, Brooke, did you get your head around that stuff? Around the way that they do the next element prediction, sampling from?
So yeah, but just because we did, a silly amount of Bloom filter stuff at Fission, right? So, right. But yeah, basically you're sampling out of this set and saying, okay, I want, I have 100 elements. I want elements 2, 16, 94, and 99. And those are what's going to go into this. I'm going to XOR those together, and those are going to go into this element, and that's 4 elements. So it's going to be stored together, count 4. And then at the next step, we're going to use basically the random number generator again to say, okay, what elements need to go in this one? How many belong in there? All of this stuff. And then we start just, again, using the same, using that bell curve stuff that we were talking about a moment ago. It's the same thing. We're randomly sampling out of our sets, and that's the number of elements are less likely. As you go further, it's more likely that you'll have fewer elements getting sampled. And so you're getting finer and finer grained as you go. And to the point that you start to just, I don't think they talk about it here, but I believe what you'll end up with at some point, way at the end, is you'll start getting single elements. Because, and we didn't talk about this either, so a major problem with invertible Bloom filters, not the rateless ones, regular invertible Bloom filters. So we looked at them very closely 2 years ago at Fission to do exactly this stuff, right? Set reconciliation. And they have this problem where if you can't get a single isolated element, you can't start pulling stuff out of it. You're stuck.
Yeah.
And then you have to say, hey, I need some other filter filter something something, right? Or if you get halfway through reconciliation and then you hit the same problem, you get stuck and you're like, well, I guess I found 10 elements and there's some other stuff in there, I guess. And with this,
and we have to start over.
Yeah, exactly.
And usually the most of the modern academia around that was start over and increase the size of the filter. So it's like, cool, we generated a whatever 5 kilobyte filter and it didn't work. So throw away most of that and generate a 10 kilobyte filter. It's
yeah. And so if as you're going from very coarse elements, like very, very compressed, very dense elements, to thinner and thinner, at the end, when you start getting single elements, that's great because now you can start getting over that hump of like, well, I hit this wall that I can't reconcile past. Oh, here's a single element. Can I pull it out of here? Yes, cool. That peels out. Oh, I can start peeling more stuff out of this stream again and start pulling elements out. So you never get, assuming that you have a friendly person that you're reconciling against. This is the Byzantine fault tolerance stuff. Then you're guaranteed that you'll be able to pull everything out with, as they call it, overwhelming probability. So it's like cryptographically, sort of assumptions, right? It's like unbelievably high probability that you're going to be able to do this. It's like, impractical that you wouldn't, in the same way that it's unlikely that you're going to guess my private key, right? Sort of level. Crap, I had another point on this. It's important, it'll come back to me. But yeah, so that's to your question, Brendan. How does this fit together? Yeah, they're just sampling as they go along. And then the algorithm, as your index increases, it's less likely that you're going to have as many elements getting shoved in there. And actually something that they mention somewhere in here as well is this also, and this was a problem that we were looking at with invertible blooms and oblivious transfer and all kinds of stuff, also sort of like in the research portion at Fission, was how would we then scale up a point-to-point sync protocol to multiple peers, right? So there are ways of doing this with Bloom filters, with Merkle trees, but even with like multiple hashing on those, you're announcing to the entire world, here's everything I have. Here's the stuff I'm interested in. Please give me everything. And as soon as you move into Bloom filters are already used for doing private set intersection, where you say, let's agree on the stuff that we know that we have in common and nothing else. So the classic case for this is syncing address books, contacts. We want to see who our friends are in common, but I don't want you to see everybody that I've ever talked to. So we both produce, one technique for this is we both produce Bloom filters. Or some kind of Bloom filter. It could be a cuckoo filter, it doesn't really matter. And then we check, okay, which elements of mine are in your sets? And then we now know, okay, here's the overlap, and we can start exchanging stuff. This has a very similar property where it's just complete garbage until you can start peeling, right? So now there are probably extensions to this, I think. Like you can already use it to reconcile from multiple peers and say, hey, we're going to probabilistically start sending stuff to me. Here's my stream. And if you match this, matching function, start sending me stuff. So basically we're going to start breaking it up into thirds, right? Take the hash of the element modulo 3, and you're going to be slice 1, you'll be slice 2, you'll be slice 3, and just start sending stuff to me. And because we're using cryptographic hash functions, these are going to be completely evenly spaced. Cool, right? And that's something really difficult to do in a lot of other scenarios, because now the communication overhead is just so high with something like a Merkle search tree, even, because now you're having to send all these layers as you're going and to discover the bottom of all of these. In this case, you're only doing this on the differences. So it becomes just way more practical to do this stuff. Yeah. Yes, yeah. So Bloom filters, for those not familiar, basically there's a bunch of techniques in this. Sorry, this is from a comment in the chat. There's a bunch of different ways of doing this and variants of it, but the really simple version is you have a bit array, and to add an element into it, you hash it n times, and that hash represents the index in that bit array. And so I definitely know that an element is not in there if it doesn't match a number of these elements, number of these indices. If I'm missing even one, it's definitely not in there. If something is in there, it's like probably in there, right? And so it gives you a way of compressing a lot of information to a small amount of space, but you give up certainty, which is what's so beautiful about this approach, is you can recover that certainty if you're willing to read off of more and more of the stream. And Brendan did a video on Bloom filters as well. So awesome.
I don't mean to shamelessly plug all of the content we fire into the atmosphere. It's just wrong. I think it'd be interesting to dig in on the BFT side of things a little bit. On the basis that like there is a bit of an asymmetry to the trust model, right? I guess this is always the case, but maybe there's nothing here. But you do get into a situation where like you really just need to have trust in the sender because the algorithm is so passive, right? Like you can just choose to like, you can get into a situation where you can just drop your recourse is basically just drop the stream of incoming elements on the floor, close connection, or yeah, that's it basically. And it is an interesting thing about this algorithm, right? Where it is very non-interactive from the synchronization perspective. You just you sort of just like start receiving bits and you start doing the work, and then both the positive outcome where you do actually invert and the negative outcome, like the paper doesn't actually define, okay, Alice has a set, Bob has a set, Bob asks Alice to send Bob's filter progressively. There's nothing in the paper that says, well, then Alice needs to go inform Bob. You can repeat that in the other direction, or you could just not, right? The end state of this is only the peer that has both their local rateless IBLT and the remote rateless IBLT XOR together is actually going to know the answer to the difference, right? That will only be the requester fulfilling the request. And so I think there is a little bit, because of that lack of interactivity, you might be able to start to firm things up a little bit from the perspective of like, it's the incentive to be dishonest is always, ever present, but at least, the number of things you can do or the places in which you can mess with the person it's relatively contained and constrained. Error case where you're going to know pretty quickly, especially based on that 1.35x the delta. Like if you have a background like, I'm syncing, my set is 10,000 items and I have received 7,000, 8,000 elements, 9,000, 10,000 elements, and I can reasonably assume that I'm not doing a full synchronization of all elements, then like, I don't know. I think there's just some heuristics that can be used here to kind of bound a lot of the Byzantine cases into situations that aren't totally catastrophic. These would all be heuristic based, like, and I see I know of no present way to like ameliorate people just jamming random GAC into the filter, right? Like there's just nothing you can do there. But at least this sort of like failure state and the positive outcome of actually inverting and recovering the 0th element, they kind of look the same from a data cost perspective. It's just when things go wildly out of whack that that's not great. I think a far greater like concern from us practically when we were looking at this is the requirement that you reconstruct the filter on any mutation. That to me is the far bigger concern. For us, we're operating in a trusted environment, like we're already using key pair backed trust. If you're in a situation where you have to trust things that the key says, this algorithm totally applies. But what is very challenging is reconstruction on every write, which honestly is not the case in many other Bloom filter constructions. It's often quite normal to say, hey, I can sort of build a set of filters that represent my content, and then I can mutate those, particularly if you want to be able to remove elements. You can use things like cuckoo filters. But here it's like a pretty hard, like, and I reached out to the author, one of the authors on Twitter, and that is the exact thing that they are working on right now. Is they are working on a follow-up to this paper to try and make some inroads on being able to mutate the filter without needing to redo everything. And so I think Li Yang was the author I was speaking with. So yeah, hopefully there's more to come here, but I don't know why I just kind of blacked out and went on a rant. I don't know if that was in any way useful.
No, super useful. Yeah. So maybe worth noting. So Byzantine fault tolerance, super high bar. It's the maximum bar for this stuff, right? And it's not, people really focus on the malicious case. It's malicious or buggy, right? And so if you can have a protocol that is resistant to buggy implementations, amazing, right? We don't have that here. Fine. But is that practically a problem, right? So like, yes, does it get complicated because you're running heuristics and all these things? Sure, it's harder, but I don't know. It depends on the exact operating scenario, right? And things that are like truly BFT, like there are things people claim are BFT that are not, right? And even then, it's like when we say Byzantine fault tolerance, we don't mean excludes any possible attack or any possible bug. We're saying we believe that the protocol should do this exact bounded thing and nothing else, and we guarantee that those specific things are going to be okay. There are other, like BFT CRDTs, for example, right? It's like we guarantee you that the structure of the partially ordered graph is going to be correct and like follow the protocol. The content in there could be complete garbage. That's out of scope, right? But it's still Byzantine fault tolerant. I think that there's maybe one way to partly, like, I'm definitely not going to claim that this makes something even close to BFT. But in terms of like, what's the heuristic for bounding one side of this? If you're willing to go up to a interactive protocol, so both parties are, quote, online, right, and active, then as the requester or as the sender, either party, if they send as many elements as 1.35 of their set size, so if I have 1,000 elements and I send 1,400, I should be able to stop, because the other side should now be able to pull out all of the elements that I have, calculate the diff, and just start sending stuff to me. So I shouldn't have to do this forever. There is a cutoff, which is also nice, I think, for the static case, because now I can generate the static. Like if somebody's going to pull from me statically, I can now just give them, hey, here's 30% more than the total set size that I have. You should be able to, probabilistically, you should be able to calculate everything out of this with overwhelming probability. And I shouldn't even have to be online. It's kind of an interesting like edge to this. And then also gives us a heuristic for, we're not going to generate data forever. We're going to generate data until whatever, 30-40% more than I trust myself, 30 or 40% more than what I have. I should be able to get to, if I'm sending, I should be able to get to this. So there's an asymmetry there. Yeah, but I think there might be interesting things to play with on that side as well. So, Brendan, because you were talking to the authors, not to put too many words in their mouths, because this is recorded, and we'll see what they say in the YouTube comments. Get in the comments, right? Were they saying anything else for future directions in this work?
Love the tweet. This is all, we work in public. I don't think so. I think it was just effectively that they were doing future work. There is definitively interest, and that they're working on removing that. They're working on being able to mutate the set. Let's see if I can find something else. I'll get back to you in 1 sec while I search.
So question in the chat for Brendan. What do you think would be cool to do with this with regards to code? I see that there's already a Go and Rust implementation on GitHub.
Yeah, on the code side, I think our team took a look at it and was like, cool, this is like nice. It's a little academic. We need to like pull in some production libraries and actually run this thing through the paces. Is definitely been our intent as a team working in the open. On the Rust side is, okay, cool. We're going to hack in there's an existing implementation, use it and measure it. And then if the measurement looks good, start pulling in much more sort of like software carpentry oriented stuff. And so I think that my recommendation, if anyone is excited to roll up their sleeves, is to go have a look at the Rust implementation and pull in sort of some of the usual suspects. Productionalizing it effectively. Getting, I don't think they're using a runtime or thinking about a runtime, thinking about what sort of transports you want to be using. A lot of this is like really kind of agnostic to that, and starting to harmonize to specific use cases and purposes. Like for us, we're using strictly 32 byte elements, right? They're always 32 bytes. And so there's some tuning, as Brooke mentioned, you can batch together these elements that you're sending over the wire. You wouldn't actually send one element, next element, and aligning sort of element to packet. That's just very silly. Instead, you would want to figure out how to sort of tune that. And from a productionalized implementation of this, I would want to see, hey, so what's your element size? And then have that fed as a generic to the construction of the library, and have that align with an underlying MTU estimation or whatever the maximum transmissible unit of a packet is. And so that you can now start to say, cool, got 32 byte elements, got packets that can be whatever, 700 bytes. How many of these can I jam into that? And like, what's the size of an element? That's the kind of stuff I would really love to see out of this work, is just to see some folks kind of take this full-throated and do a productionalized version and an implementation of this. And if we can find an excuse to work on that, we will. But it's right now, as Brent mentioned, we are currently on team Merkle-based reconciliation, and there's a number of us that have our stakeholders in that version of synchronization. And so, if we can find a way over here, that's what we would plan to do. Someone beat us to it, please. Do it yourself. It'll be done way faster.
Really, somebody please do it on top of IRO, because then we can all use it.
Not even, right? Because you could write it transport agnostic. This really should be relatively agnostic to transport. But what we'd love to see, like, I'm going to use Rust parlance, but this is true of any language. What you want to have is a stream of elements that is then properly prepped to go to the wire, such that the wire can say, I'm going to dictate that I want to consume n number of elements per thing, and then give some higher level control on the sort of resolution side of the algorithm, so that you get the thing at the other side. I see no reason why that can't be transport agnostic.
Can you hear me? Sorry.
Yeah.
So if one were to sort of think about doing it on top of IRO, or like any sort of generalized implementation, what would be like a good starting point, you think? Is just taking all of the Rust crates, importing them, and then jamming on them, or just write your own implementation from scratch, benchmark both of them, and like just what would be the best approach?
Yeah. So there is an existing, if you want to do it in terms of I know this code base well, so I can speak to it. We have a Ranger RS. So we have a set reconciliation algorithm built on top of IronNet with a benchmark suite. And we have a Rust implementation of this algorithm. And so basically you can sort of infer that you need some massaging of the two you would pull that into one. But the set reconciliation version that we wrote for IRO is also transport agnostic. But the upside is its arguments and function definitions exactly match what IRONet, the lower level transport, wants. So it'd be relatively straightforward to write a benchmark. The benchmark that you would get if you write a transport agnostic will almost exactly match what comes out the paper, modulo the language and the some of the curiosities of how you twiddle bits and bytes. But and so
Yeah,
it'd be really fun to do this over the wire. But that at that point you're now measuring the wire. So where this really matters is in context, right? Like when you're actually using this in the specific context of an application. For us, that would be IRO documents, which have a very opinionated version of sync. But we could also look at Carrier, which is another piece of technology where we are trying to synchronize giant Merkle trees, which is much more DAG looking than ours. Ours is much more set looking. And so, yeah, I don't know if that properly answers your question, but like I'll drop links in the chat to exactly where I think that would go. But
yeah, all of the code that you mentioned would be like super helpful. So
perfect. Yeah.
and just closing off, I guess. Like, do you think just implementing it in like maybe a lower level, like something like a C, for example? I don't know if there's enough support for the underlying libraries, but yeah, like just a raw C.
You can totally write this in C. Yeah, knock yourself out. If it's more useful to you, like, I mean, be selfish, right? If you can make it to fit your own use case, great.
Like my motivation is like twofold. It's just like properly, I've just graduated, so like from an undergrad researcher's perspective, I understand papers by just coding them. So yeah, the Go and Rust implementations exist, so that'd be a sort of, I think, yeah, just double work, I guess. So like, probably just like a C version and yeah, sort of learn it and then try to productionize it. So, okay.
That's actually how I worked on a TypeScript version. Is exactly that. I basically ported the Go implementation. The Go one is the reference. The authors worked from Go, and then somebody wrote a Rust port.
Great. Thank you.
But yeah, well worth it. Do it and see, and tell us about it. Tweet at us or join the next distributed systems reading group and talk about it. You spit one out and see. That would be awesome to see.
Yes. Does the group have like a Twitter handle? I don't know. I can just
Twitter,
follow.
No. But if you follow us on Luma,
okay, I can just I already follow N0, I guess, on Twitter, so I can follow you guys. Just tweet you maybe.
We'll happily advocate for your C implementation of this.
Just to 3 minutes, but just really quickly on something that Brendan said a moment ago. So at Fission, we had done a lot of stuff that was like more aware of the graph structure of the data. And so it's not that it was like application specific, it would work on any Merkle graph, right? And any DAG. And set-based reconciliation mechanisms are really nice because sets are more general than graphs. All graphs can be represented as sets, right? You can remove the structure and get sets at the bottom. The advantage of knowing about a graph structure is that you can start making assumptions that if I hit this element, I have everything before it, for example, right? So like you're doing stream reconciliation, like just purely linear stuff, like, well, I just need to know the index of where I was last at. Of course, we're doing things that are concurrent, then you don't have that, then you have a DAG. And there's nothing saying that you couldn't apply this, add another layer on top of it that became graph aware if you wanted it. That being said, because this operates on the delta, I don't know if you even need it anymore. Like versus all of the other set versus graph stuff that we were, like various teams in this space were going back and forth about 2 years ago, a year ago, 2 years ago. I think this just kind of like, this is just peace for both sides, like it just handles it. And then you can figure out the graph structure later, but on the delta. And then it also gets you on the graph side, like if something's like has a dependency way back in time, you don't have to worry about any of that. You're just like, oh, I have these elements, and then I can snap them together at higher up and break these things up into layers, which is nice. Anyway, that is my rant. We're at time. Thank you all for joining and for the awesome conversation. I will post this to YouTube later today. And any final thoughts people want on video, or should I just hit the stop button? Awesome. Thank you all. And